So hello everyone, welcome back to the 20th lecture of this class. I am amazed that we are this far. And okay, so my tablet really wants to update. I'll hope this is not going to cause any problems with the lecture. If at some point the tablet restarts, you know why. Okay, so let me recall. So we had this definition. So X is any space, a stable spherical fibration is a functor. And I usually call them S in last class, but I think I want to use V now. From X to spectra, such that for every X there exists an N, that Vx is a sphere. So that's a stable spherical fibration, and the most natural source of stable spherical fibration, as we have seen, are vector bundles, but there are others. And let me give an important example. So if M is a topological manifold, the functor M to spectra sending X to M mod, sigma infinity of M mod M minus X is a stable spherical fibration. Which I want to call the tangent stable spherical fibration. And if M is a smooth manifold, this comes from the vector bundle Tm. But as you can see, you can define this without, even for a topological manifold, without any problems. So as I was saying, unfortunately, I decided not to do the proof for topological manifolds. I'll sketch a few hints of how the proof I'm doing can be generalized for topological manifolds, but it gets hairy very quickly. And then maybe at the end, if I have time, I will give a few ideas on how you can do a different proof that is more natural in a more general setting. But for what will follow, we will need it only for smooth manifolds anyway. So I'll give you the classical proof for smooth manifolds, which is fairly easy. So, okay, and recall also we said, so E is a homotopy ring spectrum. An orientation or Tom class. Oh, sorry. No, before I say that, I should recall what the Tom spectrum is. So the Tom spectrum XV of a stable spherical fibration, V is just its colimit. And we have seen that this, in the case in which the spherical fibration comes from some geometric data, you can give a more geometric description of it. Sorry, we said homotopy ring spectrum on orientation or Tom class on V is a map, let's say XV into E, traditionally called theta, such that for every X in X, the map E tensor SVX goes to E tensor XV goes to E tensor E goes to, and that's one tensor theta, and that's one tensor the inclusion of the X component, and this the multiplication is equivalence. Ooh, sorry. I was forgetting the shift. Of course, if Vx has a non-zero dimension, of course you need a shift. Otherwise, this map is never going to be an equivalence in general. So, okay. So that's where we were left, and we gave a couple of examples of orientations. So for example, we have seen that every stable spherical fibration is HF2 orientable. And I gave a proof in the case of Z, which you can easily generalize. I think I gave it as an exercise. So a stable spherical fibration V is HR orientable. Sorry, no, I said it for vector bundles, perhaps. Yeah, let me say it for vector bundles. V is HR orientable if and only if the composite X goes to BON goes to BGL1R, and this map is induced by the ON action on the nth cohomology of the sphere. Is null homotopic. And I mean, okay, that's a very fancy way of saying that it is induced by this group homomorphism, actually. And the reason I say that is I want to mention that this formula can actually be generalized to what are called E1 ring spectra. In fact, that was my original plan to say a little bit more about its generalizes, but unfortunately I didn't manage to define E1 ring spectra. So you'll have just to live with the fact that I stated that you can generalize it. It's actually not hard. The same proof pretty much applies. But yeah, that's all I can do, unfortunately, for that. Okay, this was the recap. Questions about this? No. Okay, because I have one major theorem that I have managed to prove last time, and I owe you before I go on, which is the Thom isomorphism. So let V from X to spectra be a stable spherical fibration, E a homotopy ring spectrum, and theta from X V into sigma n E an orientation. Or a Thom class. Then there exist equivalences. So to do E tensor, which direction does it go? I think, oh yeah, this one, of course. E tensor sigma infinity plus X. Ooh, sorry, I think I'm putting the plus there. And sigma n, of course. And maps from to E. Maps sigma n, sigma infinity X plus E. So in particular, we have E lower star XV is the same thing as the reduced minus reduced cohomology. Sorry, no, not it's the unreduced homology of X, and the cohomology of the Thom spectrum is the same thing as the unreduced cohomology of X. And the shift might be wrong. I hope I'm getting it right. I think I'm getting it right. Okay. So in some sense, to understand the homology of a Thom space is the same thing as understanding the homology of the underlying space, if the space is oriented. Sorry, if the bundle is oriented. And that's what I mean when I usually say that Thom spectra are easy to get a handle on, because their homology and cohomology is accessible on some level, unless, at least when you have an orientation. Oh, and sorry, I should say equivalences of E modules, because that's also important. And in fact, of map sigma infinity plus X E modules. But that's, I don't want to discuss the module structures with respect to that homotopy ring spectrum, although it's not hard. But I'll leave it at E modules for now. If you understand the module structure for this ring spectrum, adapting the proof is very trivial. So, okay, this theorem is surprisingly easy, thankfully. Are there questions about the statement before I go to the proof? No. Okay. Let me first do the homological one. So remember, the Thom spectrum is just this guy. And theta is a map like this, which is the same thing as a natural transformation, Vx into E. Let me put the E underline, where E underline is the constant factor at E. So we have E tensor xv is the same thing as E tensor colimit x in x vx, which, since the tensor product is left adjoint and so it commutes with all colimits, is the same as this. And now remember that we have such a map. This is, let me call this theta again, and I guess this should be E underline. So E underline, and then the multiplication, which is again pointwise, and that's sigma infinity plus E sorry, it's E tensor sigma infinity plus X.
I think you forgot the shift again everywhere.
I forgot the shift again, in fact. Thank you very much. There is a reason why people mostly write it for degree 0 stable spherical fibrations, is because remembering these shifts is annoying, but you're absolutely right. One should keep track of them. Okay, so you have this map. That's definitely a map. And moreover, this map is an equivalence by definition of orientation. And well, that's the end of the proof. The other one is similar but dual. In fact, you can deduce the second equivalence from the first one with a little bit of care, but I'll just prove the second one directly. Are there questions about this? No. Good. The other one is, again, we have maps from X, V, E. Well, okay, that's a colimit, so I can plug it in and move it out. At this point, I can pre-compose with theta. And then use a map that I'm going to describe in 1 second, but sigma minus ME. And this is maps from sigma infinity plus x sigma minus ME. So what is this map? Well, we have a map sigma, we have a map actually. E goes to map E adjoint to E tensor E goes to E multiplication. And that's the map that I'm using. And I'm claiming that this map sigma minus ME goes to maps sigma ME goes to maps DXE is an equivalence for every x. And that's, well, that's because at this point we can just fix x and see that it is an equivalence. That's because tensoring by Vx detects equivalences, since it's just suspensions. It's just suspending a bunch of times, and we have, and then this map is just the same thing as the map sigma minus ME goes to, sorry, I forgot this, and that's just E, because you know, desuspending and then suspending is canonically the identity. And that's an equivalence by hypothesis. The point is that the point of this proof is that we can check stuff fiber-wise and then pass it to the co-limit or the limit, as the case may be. And so in some sense, we have translated this global statement, which is the Thom isomorphism, to a local statement fiber-wise, which is the definition of orientation. And well, that's pretty much all there is to it. No. Yeah, this theorem is important, but really there is not much else to be said for it. It's just, you know, taking the colimit of a local equivalence is a global equivalence. And that's pretty much it. And the point is, of course, that local equivalences are easier to deal with because it's pretty much about invertible E modules. And checking that some class are in pi 0 E cross, which is pretty much the content of that statement I said before. Okay, questions about this proof? No. Good. So here I will stop for a second talking about Thom spectra and pass to the notion of duality. As you will see, perhaps by the end of this class, I'm not doing these two topics together because it's fun. I think it is fun. These two topics are related, even if it might not be obvious immediately. But this is a fairly big change of topic for the moment. So is everyone okay with Thom spectra so far? Okay, good. So let's change topic and go to duality. Oh, actually I should call it with its name, Spanier Whitehead duality. Okay. Let me give first a general definition that works in every symmetric model infinity category. In fact, you can make it work even in a monoidal infinity category without the symmetry, but then you have to be careful about left and right and not be able to be careful, and we don't care anyway because spectra is a symmetric monoidal. So let me put it here. Let C be a symmetric monoidal. Infinity category, and X in C. Y in C is called a strong dual. I will simply call it a dual, but some people call it a strong dual. If there exist maps, it's called evaluation. And here I'm taking for one the unit of the symmetric model category, and co-evaluation. And commutative diagrams. X goes, let's see, X, right, X, and this is supposed to be the identity of X times co-evaluation, and then this goes as evaluation times the identity of X, yeah, and you want its brother. This goes to the co-evaluation tensor identity of Y, and this gets to Y tensor X tensor Y. It goes back to the identity of Y tensor the evaluation map. Note that in infinity category, these diagrams are actually data. I'm actually giving the homotopies, but I'm not asking any compatibility. I'm just asking that some homotopy exists. I'm not asking that they're compatible in some fancy way. They will be compatible, actually, as you will see in a moment, but it will come essentially for free. So, and that's essentially what I'm going to say in the remark. Y in C is a dual for X if and only if it is a dual in the homotopy category. Because, well, all the conditions I've said can be checked in the homotopy category. There are no, that's what I mean when I say there are no higher coherences here. Okay. So let me give you an example, just to be concrete. Let K a field, C K-dimensional vector spaces. So the dual of X is hom K X K, as you would expect. You can, and then evaluation is X, which direction? Yeah, evaluation is X tensor hom X. K is into K. This is exactly the evaluation map. That's where it gets its name. And co-evaluation, it's actually trickier. Oh, sorry, finite dimensional vector spaces is finite dimension. And as you will see in 1 second, it's very important that X is finite dimensional, otherwise a co-evaluation will not exist. And this is because when X is finite dimensional, this tensor product here is just hom from X to X. And this map is sending 1 to the identity of X. If you want, in the tensor product model is the sum of EI dual tensor EI for EI basis of X. And then it's clear that you need X to be finite dimensional for this formula to actually make sense. So that sometimes it's called a strong dual, this thing, to distinguish it from this guy that you can define for every X, even not finite dimensional. But as I said, I will just call it dual. And you can verify that these two identities here are satisfied. I'll leave you as an exercise, perhaps. And let me put a remark. Y is dual to X if and only if X is dual to Y. And that's because, well, this definition is completely symmetric. It's not true when the category is just monoidal and not symmetric monoidal, but as I said, I'm going to ignore this thing. And we have to talk about left dual, right dual, etc. And yeah, I'm not going to do that. And the other remark I wanted to, oh no, and then yeah, you say if X has a dual, it's called strongly dualizable. Again, this depends on if you put strong in front of dual or not, or rigid. This is also a terminology you sometimes see. I'm not sure what's the intuition behind rigid, but it's very common in the literature about Tanakian categories, if you've ever had to mess up with those things. Okay. Questions about this? Okay, good, because I'm going to put well, proposition, maybe calling it a theorem, is overselling it. C symmetric monoidal infinity category, X in C, and Y in C is dual to X, if and only if there exists, if and only if, there exists an adjunction X tensor blank left adjoint to Y tensor blank. So why am I saying this? There exists an adjunction because an adjunction is more than a pair of two functors. You also have to give a unit and a co-unit. And as we will see in a second, unit and co-unit exactly will correspond to giving the evaluation and co-evaluation maps. So it is additional data. But of course, we know that if a functor has an adjoint, it's uniquely determined. And so in particular, the unit, the dual is uniquely determined because it's just the value of the right adjoint to the identity on the identity. If X has a dual, it is uniquely determined. So it makes sense to talk about the dual of X. Be careful though, it's not true that if this functor has a right adjoint, then X is dualizable. In fact, in spectra, this functor always has a right adjoint, but it's not always dualizable. It's key that the right adjoint is of this form. This is not. This is important. And the proof here is just some abstract nonsense. So suppose Y is a dual to X, then we have natural transformation from the identity in C, which is just 1. Oof. I'm going to do it wrong. No, 1 tensor the identity. This maps via the co-evaluation to Y tensor X tensor identity in C. And from X tensor Y tensor the identity of C to evaluation tensor the identity that satisfy the triangular identities. Which you can, it's exactly, if you look at the definition of the relations I put in unit and co-unit, are exactly what you need to satisfy the triangular identities. Therefore, what the tensor blank is right adjoint to X tensor blank. Vice versa, if there exists an adjunction X tensor blank left adjoint to Y tensor blank, you can get F and co-F by evaluating unit and co-unit at 1. And you will see that the triangular identity forces Y to be a dual to X. Okay, so in fact, I could have taken this adjunction as the definition of a dual, but then it wouldn't be clear why this relation is symmetric, for example. This becomes clear only when you unwrap exactly what it means and you see that the conditions is symmetric in X and Y. And this is weird because in particular, if X has a dual, if X is dualizable, then it has both a left and a right adjoint, because the symmetry forces Y tensor blank to be also the left adjoint to X tensor blank. So that's a rather strong condition, in fact. And in fact, it's very strong in one categories, but in stable categories, thankfully, functors are happier to preserve limits and colimits. So it tends to be a weaker condition, and that makes it quite useful. Okay. Is what I've done so far clear? So as a corollary, I'll say that if X is a spectrum, is dualizable if and only if there exists a spectrum that I'm going to start called dual X and an equivalent, a natural equivalence, dual X tensor Z with maps from X tensor Z. That's because the right-hand side is the right adjoint of X tensor blank. In particular, dual of X is necessarily of the form max X into the sphere. So in fact, again, I am using this new notation, dual X, to emphasize that this is a special kind of dual, and it has more properties, but it's a spectrum that we knew already. It's not a new object, not really. Okay. Let me put it as an exercise here. Functor f from spectra to spectra preserves all co-limits if and only if it is of the form f of the sphere tensor blank. Therefore, X is dualizable if and only if map X blank preserves all co-limits. And the hint here is use the standard representation of a spectrum. Spectrum. In fact, we will prove this statement that X is dualizable if and only if map X blank preserves all co-limits in a minute, but this is an alternative proof. And this fact that this characterization of functors preserving all co-limits is useful. So it seemed like a good place to leave it as an exercise. Okay. What time is it? Okay, good. Okay. Now, in fact, the next thing I'm going to do is I'm going to prove this fact that a spectrum is dualizable if and only if it is finite. If and only if it is finite. And we will go in two directions. One is easy. So suppose a spectrum is dualizable. So if X is dualizable, then map X blank, which is dual of X tensor blank, preserves all co-limits. That doesn't require the exercise, it's just a remark. And therefore, X is finite by an exercise that was due, I think, yesterday, to show that a spectrum is finite if and only if map X blank preserves all filtered colimits. And since it preserves all finite colimits always. Okay. This was slightly tricky. As I said, it's very easy from map X blank preserves filtered colimits to prove that it's the retract of a finite spectrum. And the exercise I gave required a little bit of effort to show that if you're a retract of a finite spectrum, you are in fact finite. And as I mentioned, perhaps this is true for spectra. It's not a general fact. You have to actually do some work. Okay, is this direction clear? This is the easy direction. So the other direction is, well, S is dualizable. This I forgot to say. Of course, the unit is always dualizable with dual given by the unit. And and evaluation and co-evaluation are given by the identity. F coef. Okay, check. I mean, it's a very trivial tautological statement, or if you want, tensor by the unit is the identity, which is indeed its own right adjoint. That's really not a deep statement. And similarly, sigma ns is dualizable. For every n with dual sigma minus n of s. That's because, well, blank is sigma n blank, which is indeed right adjoint to sigma minus n blank. And here I am slightly tricking you in the fact that I'm using that tensor product commutes also with these suspensions. But that's because it commutes with suspensions and the suspension is an equivalence. And so it commutes also with its inverse. So it's enough to show dualizable spectra are closed under finite limits. Finite colimits, sorry. Because, remember, finite spectra are by definition the subcategory generated under finite colimits by these guys. And okay, if x, y x prime, sorry, dualizable, then x plus x prime is dualizable. That's quite clear with dual of x plus dual of x prime. And again, that this follows, quite clearly from the formula for the adjunction, if you want. Oh, actually, sorry. It's probably cleaner if I write it like this. Map x plus x prime into z. Well, that's the same thing as map x into z plus map x prime into z. and that's the dual of X tensor Z plus the dual of X prime tensor Z, and that's the dual of X plus the dual of X prime tensor Z. And now we just need to check that they're closed on their cofiber. So X prime dualizable, F from X to X prime, then the cofiber of F is dualizable with dual, the fiber of the map from the dual of X prime into the dual of X. Oh, I should have said something. 1 second, let me go here. So when I say that the dual is given by maps from X into S, this in particular implies that dual from dualizable spectra into dualizable spectra, op, is a functor, since it's maps blank, comma S. Sorry, I forgot to mention. So in fact, the dual of the map actually makes sense. Okay, and that's quite easy. Maps from the cofiber of F into Z, that's the same thing as fiber of F upper star from maps X prime into Z into maps X into Z, and that's the fiber of the dual of X prime tensor Z to the dual of X tensor Z, and that's, well, tensor Z. And this concludes the proof. And you can probably do also a direct proof for using a general colimit and not just this separating the case of coproducts and fibers. Oh, and I guess I should have said that the zero spectrum also is dualizable. I guess I forgot, but okay. Tensoring by zero is adjoint to tensoring by zero. That's hopefully. Okay. But there are some weird shifts that appear when you try to do the general proof, and I think it's cleaner if you just write it separately. Okay. Questions? No. Good. I am going faster than I was planning to, actually. So well, okay, let me put a remark first. That's going to be useful. So let E be a spectrum. Then for every X finite spectrum, we have that the homology of the dual of X is the cohomology of X in the opposite degree. And that's because that's just pi star of E tensor dual of X, which therefore is pi star maps from X into E, which is exactly the cohomology in negative degree by our definition of homology and cohomology. So many duality theorems can be obtained by identifying what the dual of a certain spectrum is. And in fact, that's the theorem I want to talk about now.
I have a question to the above proof. Where does the argument break down for infinite colimits?
Oh, it's because then you need infinite direct sums. And when you move an infinite direct sum out, you get an infinite product. And tensors do not commute with infinite products.
Thanks.
That's just, yeah, it's weird. Perhaps it's surprising, but that's how these things typically work. And when in a stable setting, the only non-trivial step typically when you want to work for all colimits is to check for infinite direct sums, which in the end boils down to some functor commuting with infinite products. And well, in this case, it doesn't. Okay. Now, let me state the theorem. Well, okay, I'll need a definition first. Okay. Let M. So now I'm going to start, you have to use some differential geometry. I hope everyone is on board with it, and stop me if I'm saying something surprising for you. So let M, border of M, a compact manifold with boundary. So let minus tangent of M to be the virtual vector bundle given by the opposite, by opposite of the tangent bundle in K0M. If you want, it's just, yeah, it's literally the opposite. I actually don't know many other ways of describing it, but this is called the stable normal bundle. And maybe later I'll be more concrete and justify why it's called like that. And sometimes I will just say the normal bundle because I forget about stable, even if I probably shouldn't, but okay. Then there's the following theorem, which I'm going to call Atiyah duality. So the spectrum sigma infinity M mod partial of M is dualizable with dual given by M minus tangent. So the Thom spectrum of the stable normal bundle. And by the way, I'm calling it Atiyah duality because everyone calls it Atiyah duality, and Atiyah actually stated the version for manifolds with boundary. But I've been told that I should actually attribute the theorem to Milner and Spanier, that did the version of manifolds without boundary, which is actually what I am going to prove now, and whose proof generalizes pretty much immediately to the case of manifolds with boundary. And noticing this generalization and the usefulness of this fact was the main contribution by Atiyah to this theorem. So let me put it. Also, well, as I said, everyone calls it always a Tia duality. And maybe I should also say that I'm following a note by Charles Resk in this. It's called the Tia duality via Frobenius algebras. I am not actually going to mention Frobenius algebras. I'm actually going to hide them very carefully in the proof. But that's a nice note if you want more details than what is going to be in my notes. And that's a corollary, which I guess I'm going to call Poincare duality. So or maybe I should call it Lefschetz duality since I'm giving the version for manifold with boundary. Let M partial M be a compact manifold with boundary. And I mean smooth manifolds here. Actually, sorry, I should have mentioned it. As I said, this theorem actually works verbatim for topological manifolds. But I'm not. I'll say a couple of words on how you can adapt this proof to topological manifolds. A compact manifold with boundary such that it is E-orientable for E some homotopy ring spectrum. And when I say that M, partial M, is E-orientable, I mean, of course, that its tangent bundle, or equivalently its stable normal bundle, is E-orientable. Then there exist isomorphisms. An isomorphism, let's see if I can get this right. The relative homology with the shifted cohomology. And maybe actually I should say that this is perhaps Lefschetz duality, because that's usually the name you give when there is a boundary. Although Lefschetz is slightly more general than these, and well, yeah. Let's cut our rabbit hole here. So proof, well, the relative homology is I guess I should say it's rather, which is what I wanted to prove anyway. But anyway, okay. This is by definition, not plus, sorry. Tensor E. That's just the definition so far. And by a Tia duality, we know this is dualizable. And so we can write it as maps it's dual. And this is a Tia duality. But now, by the Thom isomorphism, we have that this is pi star map. And let's see, the rank is minus the dimension of M. Sorry, I forgot the sigma infinity here. And that's by definition E dimension of M minus of M. And sorry, here maybe I should be more clear. When I put this E, I mean unreduced homology. Since M is unpointed, it cannot mean anything else. But that's this. And that's the end. And okay, the other one, you can prove it as an exercise, is in the other version of the Thom isomorphism. Let write it that I'm using. And so in particular, this isomorphism depends on the duality. Sorry, not on the duality, on the orientation, as you perhaps would expect. This is important. Okay, so this gives you also a proof of Poincare duality in the classical setting. If you remember from algebraic topology 1, we also had a version for non-compact manifolds of Poincare duality. These can in fact be generalized here, and maybe I'll say a few words at the end. But for concreteness sake, I'll keep thinking of this case. Questions about this? No. Okay, good. What time we have? Half an hour. I probably have enough to prove a Tia duality. Do I? Let's hope so. Tia duality, the good thing about Tia duality is that it's very geometric and very concrete. It's surprisingly geometric and concrete, in fact. So geometric and concrete that we will be able to do everything by hand. For doing that, though, I'll need the Pontryagin-Thom collapse map, because that's going to be the source of unit and co-units. Sorry, of evaluation and co-evaluation. By the way, perhaps an important remark I should make is that the proof of a Tia duality does not assume that M modulo the boundary of M is dualizable. And this is actually more important for topological manifolds. For smooth manifolds, it's not hard to prove that M has the homotopy type, M modulo the boundary of M has the homotopy type of a finite CW complex. So suspension spectrum is necessarily dualizable. For topological manifolds, it's actually also true, but I cannot think of a simple proof. And so it is kind of cool that you get that the suspension spectrum is a finite spectrum, like explicitly, because you can exhibit a dual. Okay. And by the way, it's not true, or at least I think it's an open problem, whether a compact topological manifold is a finite CW complex. That is, it has a actually finite cellular structure. It's either false or unknown. It does have the homotopy type of 1. So, oh, sorry, of the retract of 1, which is all you need. Topological manifolds are tricky. That's why I'm sort of leaving them by the wayside. But okay. Okay, it's time to define the Pontryagin-Thom collapse map. So let N closed manifolds. Oh, by the way, I'll say another thing. I'll do this proof for closed manifolds. So when the boundary is empty, and I'll say a few words how you adapt it for when you have a boundary. This is mainly for ease of notation, because carrying the boundaries around makes for a very difficult argument. I mean, not difficult, but more difficult than it is to write down already. So M closed manifolds, and F from N into M an embedding. And by the way, I do mean an embedding, not an immersion. Definition / theorem, actually. Then there exists a homotopy equivalence of the cofiber. And here by this quotient, I don't mean the quotient in topological spaces, I mean the cofiber of the inclusion. And the Thom space of the normal bundle. Of F. And by the normal bundle, if you recall, it's just the kernel of the differential of F. From the co-kernel, Necessarily the co-kernel. Yeah, it has to be the co-kernel. The other summon. And the map sigma infinity m plus into m, or sometimes also it's unstable, rather, but is called the Pontryagin Tom collapse map. And this map is obtained by taking sigma infinity to the map. This is sigma infinity of the map m plus m. And sometimes also it's unstable version without the sigma infinity. It's called the Pontryagin Tom collapse map. But since this one is going to be more canonical, and let's say also these equivalence depends only on the isotopy class of F. That's going to be important. At a key step, we're going to use that we can replace a certain embedding by another one which is isotopic to it. And by isotopic, I mean like homotopic through embeddings. I mean a homotopy, isotopy is map m times 0, 1 into m such that m times t is an embedding. Okay. That's a very concrete map, actually. So let me proof / construction. We can choose, or we can extend, rather, F to a tubular neighborhood. And by a tubular neighborhood, I mean an embedding, an open embedding, such that the composite with the 0 section is just our original embedding. And tubular neighborhoods have this nice property that they're unique up to isotopy, that is any two. So if I have an isotopy of F prime, and a tubular embedding from and a tubular embedding from tubular embedding for F and a tubular embedding for F prime, I can extend this isotopy to an isotopy of the tubular embeddings. Actually, let me write it in words, perhaps. For every H from F prime, an isotopy can be extended to an isotopy of tubular. Tubular neighborhoods, tabular neighborhoods, sorry. In particular, any two tubular neighborhoods for a given embedding are isotopic, since I can take the constant isotopy for F. And this is a standard theorem in differential geometry. I wasn't planning to prove this uniqueness of the tubular embedding. if everyone is okay with it. I'm not exactly sure when it is covered in differential geometry classes, but if you've taken a differential geometry class, you can just get a tubular embedding by using the exponential map, putting a metric over everything and put the exponential map. And then the uniqueness is essentially done by doing a straight line homotopy locally. Then, of course, what I said is not enough to get a complete proof, but it's not hard. By the way, if you need a differential topology book to use as a reference, I like a lot Kosinski book, this book here, Differentiable Manifolds by Anthony Kosinski. I'm going to use it as sort of the reference. You'll see also use it a bunch of times in the notes as a reference for all these differential topology facts. Okay, but now let's get our Pontryagin-Thom collapse map. Okay, now suppose you have a tubular neighborhood, then we have an open covering. M minus n mu f of m. That's, well, that's of course an open covering. And so a homotopy push-out square. So mu f, their intersection going into mu f, going into m minus n, going into m. And since that's a homotopy push-out square, we get an equivalence on cofibers, of vertical cofibers. Which is exactly what we wanted. And the fact that if you isotopy f, you can move nu f around, following it tells you the uniqueness of the of these of the homotopy class of this map. By the way, when you talk to algebraic geometers, this theorem is sometimes called also the purity theorem. This is absolutely not a differential geometry terminology. A differential geometer will probably not understand it if you call it the purity theorem. But since some of you might want to go towards algebraic geometry or number theory, if you see the name purity theorem, it's the algebra geometric version of this fact. The proof is very different though, because you don't have tubular neighborhoods in algebraic geometry. So you have to do a different trick. Okay, concretely, what does it mean? The Pontryagin-Thom collapse map is this map from M to N mu F. And from this description, you can see exactly what it is. It is the map, remember, this is also the one-point compactification of mu F. We saw this last time. Since N is compact, sorry, I'm talking about the space, so maybe I should use the same notation I was using last time. And so this map is just send nu F to nu F via the identity and everything else to the point at infinity. There's a remark. So if you look at how I'm defining it, that's essentially what it's doing. It's the map from this guy to the cofiber. Of course, this is not canonical at all. This depends on the choice of tubular neighborhood and everything else, but up to isotopy, it is canonical. Okay. And let's say a slightly generalization of this. I don't think I'm going to be able to prove a T duality today, actually. I think I'll finish the stuff about Pontryagin-Thom collapse maps and maybe state a more precise version of a T duality and then do the proof next time. So let V be a vector bundle on M. Then we have a Pontryagin-Thom collapse map M from the Thom space, these to M. Sorry, the pullback of V to mu F. And well, how do you do this? Well, that's just, in fact, let dV be the disk bundle of V. Just take a metric and take a unit disk. Then N embeds into dV because it embeds into M that embeds as a zero section in the disk bundle with normal bundle F upper star V plus mu F. And well, and then we have a map from dV into Pontryagin-Thom collapse map defined as before, sending the boundary of the disk bundle to the base point. And so this goes a map. Yeah, sorry, that's actually, you should put suspension spectra for the disk bundles, but okay, hopefully you can understand what I'm doing here. So I can do a twisted version of the Pontryagin-Thom collapse map. And in fact, by desuspending this map, I can define it also for a virtual vector bundle. Since we are in a compact space, so every vector bundle every virtual vector bundle can be turned into a vector bundle by adding enough copies of the trivial bundle. Okay. Is the definition of this map clear? We are going to denote this map by Pontryagin-Thom of F or Pontryagin-Thom F V if I have to make the twist explicit. Actually, I don't think I'll ever use Pontryagin-Thom F comma V, but I want to keep my options open. Okay, so that's a map. And as a remark, suppose we have W inside embedding in G inside embedding in M, then the Pontryagin-Thom of F composed with G is the Pontryagin-Thom of G composed with the Pontryagin-Thom of F, where here you actually need to put twists for this map to make sense. So you have MV goes to N, V plus mu F goes to W v plus nu f plus nu g. And that's just an immediate verification. You look at what this map is doing. And this composite is exactly the identity on the tubular neighborhood inside of W inside M, and everything else goes to the base point. Just because. Okay. So that's one map that we can associate to a map of manifolds. We also need a different map that's a lot easier to define. So suppose now f from M to M, the vector bundle, possibly virtual. In fact, it will for any stable spherical fibration on M. We have f lower star that goes in the opposite direction. This goes in the same direction as f. And that's just because it's the induced map on colimits. Okay. Questions about this? Okay, so it's time to define our evaluation and co-evaluation. And then on Thursday, I will prove you that they in fact satisfy the two conditions that we want. So first of all, I'll need, first of all, I need another differential geometric theorem, which is the Whitney embedding theorem. But don't worry, there is the weak and the strong Whitney embedding theorem, and I'm going to need only the weak one. And in fact, I'm going to need a weaker version of the weak one. So I could actually prove it. In fact, maybe I'll say a couple of words about how you prove it. So you have M closed manifold. Then there exists an N very big than 0, much bigger than 0, such that M embeds into Rn, and any two embeddings are isotopic for all m greater or equal than n. And two embeddings in Rm are isotopic. In fact, you can actually bound it. I think it's like 2n plus 3 or something like that. Sorry, to the dimension of n plus 3. It's actually very explicit, but I'm really not interested in doing minimal statements here. And the proof sketch for the existence cover M with charts U1, UR, and then such that the UI open embeddings into R dimension of M extend to a neighborhood WI. You can always do that at cost of maybe adding charts. And such that, sorry, no, don't mean extend to a neighborhood, sorry, extend to a map M to R dim N. And the extending to a neighborhood was coming from the fact that you extend it to a neighborhood and then you hit it with a cutoff function to make sure that you get to 0 outside some bigger neighborhood of UI. And then take M mapping to the product for I from 1 to R of R dim M is embedding. So, you see I'm very, very lossy, but I don't care. You could do a more refined analysis and get a better bound, but I really don't care. And the existence of the isotopy is slightly trickier. You need to show that for if n is sufficiently big, a straight line homotopy goes only through through embeddings. That's pretty much the statement. Again, I'll put references to Kosinski's book if it's there, or to another book if it's not, but I think it is. So, yeah. Okay. Okay, now that I have this, I can define the fundamental map. So let M be a closed manifold. I'm going to get a map. I'm going to get we define the fundamental map from the sphere spectrum to M minus Tm as follows. We embed M into Rm for some M sufficiently big such that any two embeddings are isotopic, or actually we don't even care. We just embed it no matter what. Then this sits also inside Sm. So we have a Pontryagin-Thom collapse map. And then desuspending it. Sorry, mu. And that's M of nu minus M, but that's exactly M minus M. And that's the sphere. And note that I'm actually jettisoning a base point here that was in Sm, but that's because the base point corresponds to S plus sigma minus M S, and the component of this map on sigma minus M S is 0. When I'll say how to adapt it for the boundary, these will correspond to quotienting out the boundary of M. But for now, this map is, even at the unstable level, it's clear, right? You put every element of the normal bundle to itself and everything else to the point at infinity. And this in particular sends the base point to the base point. And this is well defined. Because any two embeddings are isotopic. And maybe you want to embed into Rm plus 1, but then that's the same as embedding in Rm and putting 0 in the last coordinate. So any two embeddings are really isotopic, and we really don't care. So this is actually a well-defined, and this is the equivalent of the fundamental class that if you've seen it in the classical Poincare duality statement. And okay, I think I'm out of time, so I think I'll define evaluation and co-evaluation on next time, actually, unless you really, really want to see it now. But this map is a key point. This is really, really a key point. Although we'll also use Pontryagin-Thom maps for other embeddings, so that's why I defined it in full generality. Okay, I think I'll stop here. Are there questions?
Maybe a question about the earlier stuff. So about the classification we did on the dualizable objects. Can we somehow say something about dualizable objects, say in some complexes of coherent modules, quasi-coherent modules or something?
Over a ring or over a scheme?
Over a scheme. So I guess for a ring, this would
So, okay,
somehow
so these are, if you give the right definition of the ambient category, which is slightly trickier in the case of a scheme, but if you give the right definition of the derived category of a scheme.
So you mean non-separated, or what do you mean by that?
The point is, you need complexes of OX modules with quasi-coherent cohomology, and there might or might not be other additional conditions for particularly ugly schemes. But I mean that the notion of the right category, it actually has descent. There is only one that has descent, and you have to pay a bit of attention and you get it. For those are called perfect complexes. They are the complexes such that when you restrict them to an open affine, they are quasi-isomorphic to a bounded complex of projective modules. And these are exactly the dualizable objects.
Okay, nice.
And there is a similar theorem that a complex is dualizable if and only if it is compact, in the sense that mapping out of it commutes with all colimits. No, at least, okay, sorry, this is true at least for quasi-compact, quasi-separated schemes. I'm not going to, if you go for general schemes and moreover for stacks, bad things can happen. I don't want to stake too strong of a claim here. But at least for QCQS schemes, everything works exactly the way you would like them to.
Okay, nice. And maybe another question. So I read some discussion about that there's not really a possibility to universally dualize an object. That's why one inverts objects.
So that's actually a question. That's an open question that I periodically discuss with people. Oh, there must be a way of universally dualize something. And you try to write down exactly what that would mean, and you end up with something nonsensical. Oh, but then we need to fix it. And so I'm not going to say that there is no way of universally dualize an object. I'm just going to say that after many, many discussions, we haven't found one yet. Yeah. But it is a condition you can ask. You can ask, oh, is this the universal functor that sends these to a dualizable object? It is a...
Maybe a more elementary question then would be, how far is being invertible away from being dualizable?
Well, this depends on your ambient category, but in general, it's pretty far. You can see for spectra, for example, invertible means it's a sphere.
Yeah.
It's a sigma n of the sphere spectrum for some n. Well, dualizable. And in general, you should think of, for example, for modules over a ring, dualizable means it's a finitely generated projective module. Invertible means it's a line bundle. It's a rank 1 thing. So it is pretty different in general. Of course, there are plenty of categories where all dualizable objects are invertible, but they're kind of degenerate things where you don't have many objects.
So I have a question, but it's pretty far-fetched. Is there an easy way somehow to see how Verdier duality?
Oh, yes. You know what? Okay.
But we can discuss this another time too.
No, I mean, I would like to say it, but it's a bit far afield. So if someone has another question first, so that people can leave when I start discussing this. The point is, yes, there is. This is a special case of Verdier duality, in fact. So what do I mean by Verdier duality?
I have an upper shriek.
Yeah. The idea is you take X locally compact LCH, actually, locally compact Hausdorff topological space. And you can, so yeah, just to be clear, this is far afield, so if people are not interested, you can leave. I'm definitely not going to ask you about these at the exam. You can consider the category of sheaves of spectra. I don't want to define it right now, but Benedict, I know you know how to define them. And note that for those that are in the known, I mean sheaves, not hypersheaves. That's actually the big problem with the reference I know for spectral Verdier duality, that they don't have a notion of sheaf. I mean, they try to do it for hypersheaves. And so they have to add finite dimensionality hypotheses, which basically are telling us that sheaves are the same as hypersheaves. So now that we have a better understanding of that, we should be able to write it. And so, okay, if you have F, any map, you have an adjunction like this. Yeah, I guess that's, well, okay, I'm going to omit spectra from now on. Sheaves will always be sheaves of spectra. I think most of it will work for sheaves of R modules for any infinite ring spectrum R without any problem. And you can define also an F lower shriek and an F upper shriek that are adjoint in a different way. And F lower shriek has actually a fairly concrete definition in this case. What do I mean? F lower shriek is supposed to be pushed forward with compact support. So F lower shriek of F of an open U. Let me be a bit imprecise here, sorry, because I haven't thought this through and there are something in this, but F lower shriek of U is supposed to be the co-limit over all K in X proper over Y of the fiber of F of pre-image, sorry, K over in the pre-image of U. I think that's the correct definition. So sections that are whose support is proper over Y. And this turns out, and the Verdier duality is, in fact, is F lower shriek commutes with all co-limits. So it has a left adjoint F upper shriek. So I'm not sure why this is typically called Verdier duality, because the theorem that's truly a duality theorem is that when F is smooth, by which I mean locally a projection from locally 0, 1 to the n times U to U, F upper shriek of S is, I mean, the constant sheaf of the sphere is I think, sigma minus n, I hope. I might, as I said, I'm not prepared, so I might be getting things wrong. So that I would call Verdier duality for some reason is called this first theorem, but the thing that's actually making duality work is this second theorem here. And okay, and now when X, let me give a, oh, sorry, no, that's literally not, that's very much not true. By what I mean is locally constant equivalent to sigma. There might be a twist, of course. The normal bundle doesn't need to be trivial, but local is of this form. And in fact, if F from M to the point, F upper shriek of M is the local sheaf, locally constant sheaf corresponding to the manifold, to the local system. that I described before, x goes to the dual of M. Well, okay, the negative of the tangent guy. Okay, and so if M, for example, let me give if M is compact manifold, this boils down to say that the dual of M plus, well, that's by pretty much formal properties, is the global sections of the constant functor as the sheaf spectrum. So it's F lower star, but that's the same thing as F lower shriek of F. And okay, and now I am screwing up something. I want to say somehow that this is F lower shriek, F upper shriek of the sphere. Oh, sorry, yeah. Okay, sorry, I'm not prepared, so probably I shouldn't try, but you can play a game with the six-functor formalism and you get the formula for a Tia duality out of all these things. I'll say a little bit more later, perhaps, when I explain how to generalize the theorem we have said for manifolds that are not compact. In a much more restricted case.
But I see, so the geometrical input is like that you can describe the F upper shriek very precisely now with the dual as like.
Yeah.
Okay, cool, very cool, thanks.
Okay, sorry for those that maybe I went very fast and I'm pretty sure I made a mistake here somewhere because the formulas don't line up, but of course the formula have to line up since both theorems are true. Okay, sorry, I am a bit unprepared to say this precisely.
No, thanks a lot, cool.
So maybe well, I don't know if I'll leave this in the notes. I'll stop the recording. No.